recording on this computer. Okay, thank you for the reminder. Okay, so Thursday, May 14th, 2:45 to 5 o'clock. The format will be similar to the midterm. I'll provide like an answer sheet, which will just be a text file, and you'll just paste your answers into the slots that I provide. And your answers will be like, you know, a Scala class declaration, or a Scala function declaration, or a JEDI function definition, right? So you'll be pasting those in. And then you just have to upload that. You save that file, and then you upload that file to Canvas. The exam, so I'll set Canvas to like 5:05 for, you know, the last upload. So you'll have 5 minutes to get those things uploaded after the exam. There'll also be like probably almost certainly an environment diagram that you have to draw, and then you have to take a picture of it and upload that image. And so you should practice that if you haven't done it before. You know, in some computers, like if you're going to do what I do and hold up something and take a picture of it from your computer, sometimes it's like hard to, you know, on some older Windows systems, it's like hard to find what it did with the picture and so forth. So just make sure that you know how to do that. It says planning 4 to 5 problems. Yeah, that's probably right. You should have blank sheets of paper handy to draw the environment diagram. Yeah, so we're going to be asked if you can draw it in paint. Yeah, you can. You're using like a drawing program. Drawing them freehand, well, you know, if it comes out decent, then yeah, that's fine. One thing though is if you're going to use a drawing program or a painting program to do the diagrams, be really good at it, or really fast at it. You know, don't end up like spending 30 minutes, you know, trying to figure out, okay, well, how do I draw this diagram using this software? You can always just, you know, do it on paper, take a picture of it, boom, you're done. But yes, you can use software to draw it too. You'll have, of course, access to the internet, books, notes, all of that during the exam. You should make sure that you're solid. You've got like a JEDI performing properly, you know, on your computer, that there's no issue with, you know, JEDI not working. And you should understand JEDI, because I do things like, well, here's some change I want you to make to JEDI. And then you have to go right to that. Know where to go in your program, make the change, test it, and you just turn in the code that you changed. You know, it's a weird semester. You know, it's everybody's on the honor system. There will be I don't want any collaborating or communicating with anyone but me during the exam. I will set up a Zoom session for the time of the exam so you can ask me questions during the exam. I ask that if the question is real specific, you know, to do a private chat. And otherwise, you could do like a public chat, but I want everybody to be muted during the exam. Don't interrupt people by asking the question out loud. If an exam looks suspicious to me, I won't grade it. I won't give credit for it. And that means that person gets a 0 for their final exam, which is a bad thing. So that's the setup for the exam. This is a kind of a brief review of, you know, what we did this semester. So, you know, the main topic is language processing. See if this works. It does work. So I like this little picture of a language processor here. You know, this is the different phases of language processing: scanning, parsing. So scanning, this is like where we talked about regular expressions, tokens, and then parsing. This is where we talked about parsers. We introduced expression hierarchies. We did this for a number of languages. Uh, and then the parser is going to take these tokens coming from the scanner and turn it into some kind of an expression. We sometimes say that the parser, the output of the parser, is a tree, and you could kind of see that, right, with the Scala parsers. They generate these weird data structures, tree-like structures, and then we had to write transformers that would take out the pieces of this thing and turn it into some kind of an expression, a fun call, a conditional, an assignment, whatever. We didn't take this route up here, the compiler route. That's more of a 153 kind of topic, translating into assembly language. But I forgot the type checking. Yes, the type checking then goes through all of the sub-expressions and associates a type with each sub-expression. Okay, this is what we talked about the last day of class. And then once all of the sub-expressions of types, then we can assign a type to the expression containing those sub-expressions. So you imagine you've got a tree of expressions. At the bottom of the tree would be literals. And then, so we work from the bottom of the tree up and, assign a type to each node based on the types of the nodes underneath it. And one possible type that we could assign as the failure type, indicating there's some sort of a type error, and then everything fails in the tree above that point. So that's what type checking looks like. And that's not going to be covered on the final, by the way. And then, so then we have this type check tree, and then that goes into execute. And that's where we have all of our execute algorithms distributed throughout the expression hierarchy. So that is sort of it in general. Some of the concepts that came up, so really important expressions versus variables, values rather, sorry. Expressions versus values. So expressions, what we type into the interpreter, values are what get typed back at us. Those are our two fundamental hierarchies for Jedi. Variables versus constants. So we actually have a variable value in Jedi. Sequence control, so selection, iteration, escape. So conditionals, for example, in Jedi. Iteration. We didn't really do escape in Jedi. That would be a good exam question. Declarations, so that's definitions. The bindings they create, they put them in an environment. And then we had like the static scope versus dynamic scope. Where is the binding visible? We didn't talk much about lifetimes, but how long is the binding, is the environment a temporary environment, or does it persist? Does it get garbage collected or not? So that's what lifetimes refers to. Talked about regular expressions and scanning, asking if something matches a regular expression. We talked about grammars and parsing, and of course, execution algorithms for all of the different categories of expression. Lazy versus eager executions, we did a lot with that. Conditional and short circuit execution were forms of lazy execution. We had blocks. Qualification just means qualification principle, the software engineering principle that says the scope of a binding should be as small as possible. So that's where we can create, we can define something in a block, and that binding that definition creates is only visible in that block. Abstraction principle, being able to give a block a name, and that is, and to delay the execution of that block until the name is invoked. And so that's what lambdas and closures were for, and also texts and thunks later on. Static versus dynamic scope rules, again, this distinction, parameter versus operand versus argument. I hope you know the difference. Parameter would be like what goes inside of a lambda, X, Y, Z. That's what the lambda refers to its input as. The operand would be the input as an expression. The argument would be the input as a value. Operator precedence and associativity. Multiply has higher precedence than addition. Addition and subtraction are left to right associative. They have the same priority. So how do we decide if there's two subtractions in the same expression, which subtraction goes first? Funcs, text, and parameter passing mechanisms, passed by name, passed by text, passed by value, you should know. Paradigms, we spent a lot of time talking about the functional programming paradigm, which features tail recursion, combinators, generic functions, closures, list processing pipelines, and then the object-oriented paradigm, which features traits, interfaces, inheritance, singletons, polymorphism, inheritance, stuff like that. We didn't really talk much about imperative paradigm. That's the one that most resembles, assembly language. We have variables, commands, blocks, procedures, and modules. We didn't talk much about that. And sadly, we didn't get to logic programming, facts, rules, queries, inferences. And then some features of Scala. I'm not going to read through this. You can read through this yourself. But what did we do? We did the ones that you have to worry about: object-oriented programming in Scala. Yes, that'll definitely be on the final exam. List processing will probably be on the exam. We have these list recursion, tail recursion, iteration, and then pipelines using map, filter, and reduce. So that'll be on the final exam as well. And of course, parsers and regular expressions in Scala. And then JEDI, we had context values and expressions, the different kinds of expressions. And I will ask you a question. Write a simple function in JEDI. And don't get mixed up when you see that. It's not a question about changing the JEDI interpreter. It's not I don't want a mixture of JEDI and Scala, right? Just a pure, like if you were a JEDI programmer. There will be pre-midterm stuff. I have a link here. Let's see, make sure it works. To the midterm review, I think. Yeah, there's the review, the midterm, and the solutions. The kind of thing that will come up from before the midterm, as I've said, is write a combinator or write a list processing function. My perfect one is a combination of, like, you have a list of functions, and you're supposed to take this list and do something, with the list of functions. Maybe produce a more complicated function and return it. Okay, so environment diagrams. I am going to come back to this question later because I'm not sure I have the solution posted anymore, so I might have to do this solution by hand. So let's start with problem 2 here. Okay, so break. Scala doesn't have break. It's kind of, they do as a kind of a weird break. And I think it's kind of a shame. I'm not sure exactly. I'm sure there's some deep intellectual, philosophical reason why they don't have break in there, but I was sort of sad to see break go. So let's add break to JEDI 3 on the final exam. So here I have x has got 0 in it, while it's a variable containing 0. While the content of x is less than 10, I'm going to write the content of x. I'm going to increment x by 1. And then when the content of x is equal to 5, I'm going to break. And here's the output produced. 0, 1, 2, 3, 4. These are all side effects, of course, produced by the write statement. And then boom, we're done. what happened? X equals 5. We thought we were going to go up to 10. Well, as soon as we reached X equals 5, we broke out of this loop. So break is now a new expression that's being added to, that you have to add to Jedi 3. And I've broken it down here. So you implement a break exception class. The way it's going to work, I'll just give you a little preview of it, first of all, is that in our iteration execute, when we come across a break, break is, the way you execute a break is you throw a special kind of exception that's going to be caught inside of the execute for iteration. And so can't be just any kind of exception. So we're going to create a special kind of exception class for break to throw. And then a break will be a special form that simply throws a break exception. Okay, and then you're going to implement a parser for break. And here's the syntax for break. What could be easier than that, right? And then part B, modify the execute method for iteration so that it terminates iterating if the body executes a break command. Okay, and we're not going to use the break command that Scala sort of has. Okay, now I think I have that maybe down here. Let's see if it's in my answer sheet. Okay, so this is what my answer sheet will look like. You know, like here's like number 2, paste in your code here. Right, so here is my break exception class extends Jedi exception. I don't need to put a message in there or anything like that, you know, because it's not a real error. And here's my break class. This is extend special form. It's a case class. By the way, you do, if it's a case class, you do need some, even if it's an empty parentheses, that is required there. And then here is execute, which throws a new break exception, and I have to return something, so I'll return a notification break, although we'll never get there because we throw an exception before that. And then do I have a break parser? Here's the break parser here. This is a parser that returns a break. If the thing looks like a break, then we just return a new instance of this break class. And then here's iteration. So this is the hard part. So this is iteration that we have so far, right? And you know, let's go through this. Here's the condition of the iteration, and here's the body of the iteration. So here I execute the condition to get C1, its value. I check to make sure if it's not an instance of bool, I throw an exception, a type exception. Here I cast C1 as a bool. Okay, and now I'm going to set break, a special flag, break flag equal to false. Where is the break flag? Oh, it's declared right here. Okay, so while C2.value, that's true, right? That's Scala true, and not break. We haven't broken yet. We're going to try this. We're going to try to execute the body, okay? If it throws a break exception, then I'm going to set break equal to true, okay? And we're going to come around here, break will be true, and we'll get out of the while loop. And then, shoot, I also put continue exception here. So this must have been for a continue. So I guess I can't give you that for the exam. That would have been a good one. If it's a continue exception, we'll do nothing. So we don't have continue yet. And then we re-execute the condition because that might have changed. And then we return done. So that's how we translate. If something in the body of this while loop, you know, this could have been a block or something like that, and we're executing, and then one of the things in the body was a break, then break would have thrown a break exception, which we catch inside of this while loop in Scala. And we use that to set this break flag equal to true, and that terminates the while loop. Okay? You could have probably done the while inside of the try too, I suppose. So there, what I'm trying to do, and I'll do this on the real final, is I try to, I don't just say implement break in Jetta, that would be too hard, but I'm trying to like walk you through it, and give opportunity to give you partial credit for the different parts of this. Okay, problem 3, Jedi programming. In Jedi 3, implement and test the following functions. So here I have exponentiation base 2 using iteration, not using recursion. Okay, and then here is rem nm equals k. This is the remainder function. K is the remainder of dividing n by m using integer division. So for example, remainder of 14, 5. Well, if you divide 14 by 5, it goes in 2 times remainder 4. So k would be 4 in that case. Okay, and then this is where you have to be careful. Like I've given this question in the past, and number 1 answer is you do the implementation in Scala. And I can't give you any credit for that, even though it might be a correct implementation. Number 2 mistake that I see on this problem is that you put exponentiation base 2, you make that a new ALU function. No, that's not what I want here. You are now a Jedi user, not the Jedi implementer. So we sold off Jedi to Google. It decided they're going to use Jedi for all future development. Right? And so now you're like a programmer at Google, and somebody says, okay, implement 2 to the n power. You don't have any access to modify the source code. Let's see if I did this one. Okay, so this is exponentiation base 2. Okay, this is how you'd have to define it, lambda n. Okay, and then what I've done is I set up 2 variables. So here is the result, a variable to store the result in, and a variable to store the count in. How many times do I want to have to do this? Now, while the content of count is less than n, and then here I'm going to have a block, I'll increment count, and the new result will be 2 times the content of the old result. I'm assigning that to result. And then I return the content, or not result. Remember, result is a variable. It's the content of the result that I change. Okay, and unfortunately, I'm going to be fine if you want to turn in your definition in this form. You can't test your definition in this form because the formatting, my reader doesn't know how to do formatting. So by that, I mean the console doesn't know how to understand, treats every line break as the end of an expression, starts parsing it. So, but you're welcome to format your definitions when you turn it in like this. That would be helpful for me, but not required. Here's the remainder. And let's see, this looks pretty tricky. So it's a lambda. It takes 2 inputs, n and m. If m is less than n, so again, maybe n is 14 and m is 5, okay, then the answer is n, okay, so that would be 14 minus m times, and then this should be n divided by m. This is kind of a cheat. This is integer division in Jedi. So I'll do 14 divided by 5. This will give me 2. 2 times 5 is 10. And then 14 minus 10 would be 4. And then there are a couple of different ways you could do that. Okay. Here's another interesting Jedi programming problem. So this wasn't assigned, but you saw it flash by. It's the Jedi 2.1 feature, which is that we have this flag that you can set to change Jedi from the static scope to the dynamic scope rule. I think static scoping was the flag, and it's set to true. If you set it to false, then dynamic scoping is used. Okay, so now suppose you're programming in Jedi and you're running Jedi and you don't know how that flag is set. Maybe you don't have access to the source code, whatever the reason is. So you're wondering, well, I wonder if this Jedi that I'm using is using static scope or dynamic scope. So here we have to write a Jedi function that returns true if static scope rule is used and false if it isn't used. Okay, so I like this kind of a question. You have to think about it. First of all, let's think about the difference between static and dynamic scope. So static scope says that when you're executing the body of a function, you execute that body relative to the defining environment for the function. The dynamic scope says, no, you execute the body relative to the calling environment for the function. And so what you have to do here is you have to set up a situation where the calling environment is different from the defining environment of some function. There's a couple of easy ways to do that, right? You could define the function in a global environment and call it inside of a block, which has some temporary environment. Or the other way around. You could define the function inside of a block and then call it in the global environment. So either way works. And there has to be some difference between the calling environment and the defining environment that affects the value of the function. Oops, I think I have to scroll down. I can just line that up again. So here I define a constant is static. So this is in Jedi, we're at the prompt. I define a global variable is static is equal to true. Okay, and now I'm defining a function called test. This is a function that takes no inputs and it returns is static. Okay, so test is defined in an environment, it's defined in the global environment where there's a variable constant is static, which is equal to true. Okay, and now I'm going to create a block. And in this block, I have a local variable is static, which is false. And then I call test. Okay, so let's think about this for a second. Maybe I could even draw like a picture of it. Let's see, test. It's a closure. So this is the picture. This is the environment diagram. This is the global environment. Let me indicate that. Okay, so after I've defined test, A test is bound to a closure. The body of that, there are no parameters. The parameter box is empty. The body is static. And the defining environment is GE, the global environment, and is static is set to true in the global environment. Now, I'm going to create a block, which creates a temporary environment. Which also has something called is static in it. And then I'm going to create the temporary environment for I'm calling test. So here's the situation. So we go into a block. Block sets up a temporary environment, TE1. And it has is static in there bound to false, and it extends the global environment. Now, relative inside there, we're going to call the function test here. Okay, that sets up a temporary environment. Let's see, my finger's over it. TE2. I guess TE2. There's nothing in that environment because there are no arguments, no parameters, no arguments. And then you see there are two DE arrows or two EXT arrows. So if static scoping is used, then this TE2 environment here, he's going to extend the defining environment of the closure, which is up here. And so he's going to return this is static. He's going to return true. On the other hand, if it's dynamic scope rule, he's going to extend the temporary environment created by the block, TE1. He's going to return is static, is false. So that's kind of a slick way of doing it. You know, it doesn't have to be slick, it just has to be right. But, you know, you should be able to, I mean, I do this kind of question. You should be able to set up a situation. You have to understand the difference between static and dynamic scope, and you should be able to set up situations where it makes a difference. Okay. I mean, it would be great, like during a job interview, if somebody asked you, well, what's the difference? And you could like set up some little situation like this. You should be able to do it. And the way I used to ask it was for Scala. Maybe there could be some flag dynamic scope for Scala. How would you do it in Scala? How would you test whether Scala is dynamically or statically scoped, if you didn't know? Okay, moving on. So I'd like to ask like some sort of like, I like questions about object-oriented programming, and especially the kinds of questions that involve like simple programming languages, like baby versions of what we're doing with Jedi, right? And forgive me if we've done this one as a homework problem, I can't remember. So accumulator is a simple machine, executes commands that update a fixed variable. And here it looks like I'm giving you the code for accumulator. That seems very nice of me. So here is the fixed variable accum. Accumulator, notice, is a singleton. Okay, now, and then it has this execute, which takes as input program, which is, and this is what's called a var-arg in Scala and Java. So command star means that program is just a sequence of commands. And that sequence of commands, so when you call it, you can call execute A, comma, B, comma, C, comma, D, or A, B, C, and D are all commands, and it's going to take A, B, C, D and group them together as some kind of a sequence, an array or something like that. So program, when we go inside of execute, will actually be a sequence, an array of command objects. So we set the accumulator to 0. And now for each command in here, we execute the command. And that presumably, executing a command presumably is going to update this accum variable here. And then when we're done, we return whatever the content of accum is. Okay. And here are the accumulator commands. So we have a command trait with an abstract execute method. And we've got add. And so this value is the value that we're going to add to the accumulator. We've got multiply. This value is what we'll multiply it by. Set. We'll take this value and assign it to, simply assign it, sets the accumulator value to whatever value you want. And then iter actually has, let's see, iters. So iter contains a command, and it's going to execute the command iters number of times, I think. Oh, okay, I guess that makes sense. So for example, here's the accumulator.execute, and here are the commands that I'm feeding it. So this is going to set the accumulator to 2. It's going to add 3 to 2, so 2 plus 3 is 5. And now here, iter, I'm going to do the multiply to command 5 times. So what was it, 5 times 2 is 10, times 2 is 20, times 2 is 40, times 2 is 80, times 2 is 160. Okay, and then it's going to return like 160 for the answer. Okay, and now here's the thing. I mean, I don't know how good you are at reading these UML diagrams, but notice that like, for example, the add command here, this is the value you want to add to the accumulator, but none of these guys, there's no pointer over to the, there's no pointer to the, what's it called, the accumulator itself, right? So when I execute this thing, I'm going to be adding this value to this variable right here. But how do I get there? How do I navigate there? There is no pointer here to the accumulator. And I have this little warning, follow the class diagram carefully. So you can't smuggle a pointer in there. You can't smuggle in anything. Okay? And so here's the thing that I want you to take away from this. Remember that Scala doesn't have static. Okay? Without this, there's no concept of static. You can't use the word static, declare something static. How come they don't have that? Well, they don't need it because they've got singleton objects. When you declare a singleton object like accumulator here, okay, it is static. Okay, it is static means it's global and it's public. Okay, since it's global and public, anybody from anywhere in the program can refer to the accumulator. It's a global public variable, visible throughout the entire program. Furthermore, static means that anything that's allocated in static memory, so there's a special memory segment for singleton objects for static stuff in Java, C++. All of that static stuff is created before the program, before main is called in the program, the very beginning of program execution, and it lives until the program ends. Okay, so that's the important thing, is that these objects, these singleton objects, are global and public. You can reach them, you can refer to them from any other part of your program. You don't need a pointer to them. So let's see how that got used. So for example, here's my command trait. Command knows how to execute itself. Okay, and then here's add. Oh, and you're supposed to notice something else you're supposed to notice. Notice, for example, when I say add 3, I'm making an add command with value 3. I want this to look like it's a real command, so I didn't want to write new in front of there. So I don't write, it's not new add 3, it's just add 3. So what I did was I made this a case class. Remember, case means, among other things, that it automatically generates a companion object with an apply method in it. Okay? And then here is the value to be added to the accumulator. It's a val, not a var. Remember, use var, only use var if it's necessary. And it extends command, which means I have to now implement execute. And here, accumulator.accum plus equals value. So that's exactly what I meant. Again, accumulator is a global object. I can refer to it from anywhere in the program. Multiply is the same, set is the same, and then let's take a look at iter. Okay, so here is the command you're supposed to iterate, and then iter is here is the number of times you iterate it. So for I equals 0 until iters, command.execute. Super easy. And here's the accumulator, which I already had. So I like this. Test your knowledge of like some of the weird, cool things that are available in how object-oriented programming is different in Scala than it is in Java. We have traits, we have case classes, we have companions, we have singleton objects. So we're like ringing a lot of bells there, and that's what I love to do. Is I like to ring a lot of bells. Should have been a fireman, maybe. Count roots. Okay, so this is a Scala function you have to implement, and this would be an example of a pre-midterm kind of question. Okay, so it has 2 inputs, f, which is a unary function with return type double, and inputs, which is a list of inputs for f. The output of count roots is the number of inputs x such that f of x is approximately 0. And then for full credit, we'll implement count roots without using iteration or recursion. So the way I would write it, this is an old question, the way I would write it now, it's using a pipeline. Okay, and your solution should be as generic as possible. Yeah, okay, generic as possible. Okay, pretty slick looking function. So here is the function that we're counting its roots. To be generic, the domain of this function could be anything at all. It could be strings, integers, whatever. And so I'll call the domain T, and T will now be like a parameter. Count roots is a generic function. But we did specify that the output type should be double. And then inputs, these are inputs for f. So this has to be a list of T, whatever the domain is. Okay, and so now what I'm going to do is, here's a pipeline solution. Inputs.map of f. So I'm going to hit each input with f. I'm going to transform each thing in the input list into a double using f. Okay, and now I'm going to filter it. And my filter test is you're good if you're equal to 0.0. So underscore equals 0.0. So anything that's not 0.0 is going to get filtered out. And then what's the size? How many things do I have left? Okay, let's try that again as maybe a, hang on. Maybe let's try that in a slightly different way. All right, I guess we could do it as a, let's do it as a Scala worksheet. The signature looks the same. Is that right? And then let's just try tail recursion just for like old time sake. Right, so the way I do tail recursion is I define an internal helper function. Okay, it has two inputs to it. The result and the unseen elements. And it's going to return an int. And then when I call helper, the result, well, as far as I know, there are no roots in there, so 0. And I haven't seen any elements yet. That'll be my return value. And then it's helper that's going to be tail recursive. So if I'm on autopilot at this point, you know, the stuff that I'm typing in here is just boilerplate code, right? So I'll have something here, and then I'll have unseen dot tail. And so then, and it's tail recursive, as you can see. So what will the new result be? Well, it'll be the old result plus, well, if unseen, if f applied to unseen dot head 0, let's make that 0.0, then we found another 0. So I'll return 1, else I'll return 0. Unseen. Oh, this is not a list of double. Yikes. Sorry. This is a list of T. And then you could test it like here, oh, let's make a function. Okay. So here is just a little test function. And you can see, I'll make that 3.0, 4.0, I don't know if that's necessary. But you can see that the roots of this are going to be 3 and -4. And then you can do count roots. And then we'll make a list. Let's see, we'll put 5.0 in the list. We'll put 3.0 in the list. We'll put 4.0 in the list. We'll put -4.0 in the list. And maybe add 0 to the list. Save it. Count roots returns 2, because in this list, 1, 2, 3, 4, there are 5 things in the list. 2 of them, -4 and 3, were actual roots for foo. Okay, so, and that is tail-recursive. Why? Well, helper is recursive because helper calls helper, but the recursive call here comes at the very end of helper. There's no pending work that has to be done out to the value returned by helper. The value returned by helper is a value returned by helper. It's not helper, you call helper and then you add 1 to it or something like that. That would be traditional recursion. So something like that would be a good pre-midterm kind of question. So here's another one, sort of a pre-midterm kind of question. So the instructor wants you to automate grading student submissions. A submission is simply a list of answers of type option T. So this is like an option question. For example, an exam asks students to solve 6 algebraic equations. Here are some solutions submitted by student Smith. Okay, so he's got, let's see, so he was able to, there were 6 problems, okay, and these are his answers. So his answer to the first problem was 1.3. We don't know what the problems are, right? But it's some 1.3. The answer to question number 2 is 2.1. So we have some 2.1. Smith skipped problem 3, so the answer was none. His answer to problem 4 was 55.9, and then he did not submit answers to problems 5 and 6. Okay, so then the instructor wants you to implement a Scala function of the following form. So we're going to grade, grade. Okay, and it has, here is the submission of Smith or some student, which is a list of option T. Okay, here's the model solution provided by the instructor. Okay, it's this is what the answer should have been. And then here is a function close, which takes the student answer and the instructor's answer and returns true if they're close enough. Okay, and it's going to equal the score. You know, how many answers the student got right. Let's take a look at the code for that. So here it is. Okay, so this looks like it's going to be an iterative solution. So we set the score equal to 0. The student Smith hasn't gotten anything right yet. And so now we're going to iterate through the model solution or we're going to iterate the length of the model solution. So remember, the model solution is going to be complete. If there were 6 questions on the test, its length is going to be correct. Okay, and then here I'm using one of these guards. If I is less than submission length, and submission sub I is not equal to none, okay, so those 2 conditions have to be true. then he gets submission sub I dot get. Okay, so now what does get do? Well, if it's an option, so if it's a sum, then get tells you what's inside the sum. Okay, so it was like sum 3.1, then get would return the 3.1. So that's getting the student's actual answer, right? We don't have to worry about none because we're skipping over the nones here. And here's the instructor's answer. And so if it's true that they were close, then score gets incremented by 1. And then he returns the percentage. 100 times the student score, and this was the number of questions asked. So the student got 3 right, then his score is going to, out of 6 questions, and his score is going to be 50. Next, the instructor wants you to implement a Scala function of this form. So average takes submissions. Now, this is crazy. This is for the whole class. What we saw before in part 1, this is one student submission. So this is a list of lists of options. So these are the submissions for the entire class. Here's the model answer. Here is close. Okay, and what this is going to return is what was the average score for the entire class. That is way down here. Lift it up so I can see it. Let's see, the formatting is a little weird. Improve it a little bit. So here's the average. Here are all of the submissions. It's a list of optional values. Okay, and so what I'm going to do is submissions.map. And here is a special function called sub that I'm defining. Sub takes a list of optional values and it returns the grade for that. So why did, sub means submission. Okay, so this is a map. Remember, this is a list of submissions. So it's going to apply the grade function that we just defined to each submission in the list. Okay, so the output of this map up to here, the output of this map is going to be a list of the grades for each student in the class. So we've got a list of submissions, and we've transformed it into a list of grades. Okay, and now we're going to reduce that list using the plus functions. We're going to add up all of the grades of each student, and then we'll divide it by the number of submissions there were. And that should give us the average score for all of the students. And then here I give you some tests for this thing. And then you're good enough if it's in. So this is how to test it. You know, looking at this, probably this problem is a little too, it's not that the coding is hard, but it's a little too complicated for the final exam, I think. It takes too long to understand what the problem is. So it's probably, I mean, I love the idea of lists of options or lists of options. You should certainly understand what an option is. Okay, and then finally, let's go back up here because I didn't post the solution for this. I don't think I did. Let me just quickly check and see if I've got that somewhere. Hang on. see. I don't see it. Hang on 1 second. Let me just see if I can bring it up another way. No, I don't think I do have it. So I'll just have to work through it and post an image of it for you. Let's look at the problem again. So this is an environment diagram. And we make 4 definitions, A, B, bar, and C. Okay, all of these definitions are at the prompt. So A, B, bar, and C are going to go into the global environment. So let's see if I can do that. A second, I have to get some liquid on this. Okay, so I'm drawing global environment. A is 10, B is 20, and bar is a closure. It's got parameters X and Y. It's got a body A plus, is it X plus Y? And its defining environment is the global environment. Let me dry this off a bit. See this, it got a little bit smudgy. Stop the share for a moment. So you can do speaker view maybe. So you see the global environment. I haven't defined C yet, but you see A is 10, B is 20, bar is a closure. That's this guy here. The closure, the parameters are X and Y. The body's too tiny to see, but I think it says A plus X plus Y. This bar was defined, the current environment was the global environment. So here the defining environment in which closure was created was the global environment. Okay, next, I'm going to define C. So C goes in the global environment, so it's already there. But look, it's a block. So we now go into block.execute. You know, when you go into block.execute, you create a temporary environment. I'm going to create an environment TE1. That temporary environment is going to extend the global environment, and it's going to have the binding A is 5 in it. This is what we're looking like now. You see down there TE1, can't see it. It's got A equals 5. This is just block.execute. It's got A equals 5 in it. And it extends, well, at the time, the current environment was the global environment. Now the current environment is TE1. And then there's a block inside of a block. So that's going to create yet another temporary environment, TE2 we'll call it, which extends TE1. And what's it got in it? Well, it's got B equals 2. Now this is what the picture looks like. TE2 extends TE1, a block within a block. Now we're calling bar of AB. Okay, so first question, so we go into funcall.execute. The first question is, well, what are A and B? What are the values of A and B? Right, and you can see by both the code and looking at here that if you're in TE2 and you're saying what are A and B, you're going to get A is 5 and B is 2. That's the eager execution part, remember? A is 5, B is 2. So we're calling B of 5, 2 now. Okay. Next, I'm sorry, bar of 5, 2. Next, if in funcall.execute, you ask, is bar a closure in the environment? And yes, it was, right? It's in the global environment. It's the closure created by that lambda. And now, finally, we're going to do closure.apply 5, 2. Okay, and so now we're in closure.apply. It creates a temporary environment, which I'll call TE3. And TE3 puts in bindings for the parameters of bar. Now, the parameters of bar are X and Y. And the bindings are the arguments are A and B, 5 and 2. So now here's what my environment diagram looks like. I'm going to stop the share for a moment. Again, if you put it on speaker view, I can't put when I do mine on speaker view, I don't see myself, but somebody else that I don't understand why, but I might as well have it in gallery view. So TE3, that is the temporary environment created by closure.apply. The parameters for bar were X and Y, and the arguments were 2 and 5. So now the question is, well, where do I connect TE3 to? And remember, static scope rule says, well, you connect it to the defining environment, which is the global environment. So I will do that. So notice at TE3, it's put the wrong letters in there. Don't go away, don't go away. EXT. I'm not taking the final. So notice that TE3 created by apply, it extends GE because that's what the closure, remember the closure remembers its defining environment was GE, so that becomes the environment that's extended by TE3. And now I just do the math down here. The body of bar was A plus X plus Y. My writing's terrible. A plus X plus Y. Okay, well, A is going to refer to A equals 10 up here. Okay, so that'll be 10 plus 5 plus 3, which is 17. And now ask yourself the question, well, what if dynamic scope rule was used? If the dynamic scope rule was used, Well, then the calling environment, this extends the calling environment, which is TE2. So the arrow would go, this would extend this. And now we're going to get a plus x plus y. Well, x plus y is going to be 7 still, but we're going to pick up this a over here. 7 plus 5 is 12. Okay, so we get a different answer. It's not a question of which answer is right and which answer is wrong. I'll try to take a snapshot of this and upload it. It's not that one answer is right and the other answer is wrong. It's you know, I guess which answer, you know, makes more sense, you know, in the context of programming. Probably the static scope answer makes more sense than the dynamic answer. I think, you know, we talked about the problems with dynamic scope rule, which as far as I'm concerned exists mostly just to torture students like you. Okay, that ends the review. Now, some of you might be looking at all of that and thinking, you know, my God. But remember, it's not going to be all of those questions, right? I mean, I gave you, I don't know, 7 or 8 questions on the review. It'll be, you know, maybe 3 or 4 questions. I don't think time will be an issue for you on the exam. You'll be working in the comfort of your own home. I'm hoping your home is comfortable. You know, chase everybody off the internet while you're doing your exam, so you won't have upload problems. I went to a thesis defense yesterday, and you know, the guy kept breaking up and breaking up. We couldn't hear. It was like on Zoom, and I finally thought to ask him, you know, is anybody else in your house on the internet? He goes, well, yeah, 3 people are on it. So I said, go kick them off. And he did, and that fixed the problem. So, so yeah, try to get exclusive use of the internet during the exam. And yeah, there aren't going to be that many questions on the exam as there were on the review. Some of those review questions are a little bit, you know, I hope to do better on the exam. You know, those questions will be a little bit sharper, you know, a little bit easier to understand. You know, I'm not interested in having you write tons and tons of code or some complicated algorithm. And this is a concept class. So I'm interested in your knowledge of the concepts like dynamic versus static scoping, and, you know, is your knowledge solid enough that you can express them in code, and specifically in Scala. Questions? A few. Yeah, somebody asked about office hours. That's a good question. Let's see. So when is the exam? The exam is Thursday, is it? Thursday. And I think I have, let me just check the 151 exam. That's Wednesday morning. So let's see, how about if we do, let's see, I lost everybody. Yeah, let me think about it. So I promised that I'll have Friday and Monday, of course. I will probably schedule an office hour for Tuesday and then maybe schedule an office hour for Wednesday. Okay, but let me sort that out first. I don't see any reason why I can't do that. Let me just check my calendar real quick. Oh gosh, now my phone is offloading all of my apps for some reason. Wednesday. The exam at 9:45, curriculum committee at 1. So yeah, it would have to be probably like, probably do it like around in the afternoon, late afternoon on Wednesday. But Tuesday, I'm free all day Tuesday, so I'll figure something out. Probably 10:30 on Tuesday, and then maybe something late afternoon on Wednesday. Okay, anything else? Okay, then I will see you guys during office hours, and if not, then next Thursday during the exam. Bye.